All right, so I'll discuss about primed one factors and some recent results, and with the emphasis on actions when they come from actions of product groups. Before getting into the business, let me just start with a very basic definition and some other basic definitions. So a phonema algebra is just an algebra of bounded operators on a Hilbert space that is closed under the adjoint and in the weak operator topology. So in the coefficient topology. So Ti goes to T in the weak operator topology. If whenever you have two vectors, Ti xi inner product with eta will converge to T xi eta. And very fast phonema algebras can be seen to be B of H itself, the algebra of all bounded operators on a Hilbert space. And once you have a measure space, you can look to L infinity of x, and this will act on L2 of x, and again you get a Neumann algebra. Classes of Neumann algebras that were very studied go actually back to the work of Moyer and von Neumann. They show that to any countable group, you can associate in a natural way a group Neumann algebra denoted L of gamma. And I will just quickly sketch the construction. So we consider the left regular representation denoted lambda g. And lambda g acts by left shifting on the Dirac masses delta H. And if you look to the group algebra C of gamma, L of gamma is just the weaker operator topology closure. In a similar way, you can get a phonema algebra from a group action. So if we consider gamma acting on X a measure space, measure preserving action, we denote the so-called group measure space for Neumann algebra. We denote L infinity of x plus gamma. And I can simply say that, roughly saying, it's generated by a copy of L infinity of x and a copy of L of gamma previously defined. And they satisfy this covariance relation. So the lambda g's are actually normalizing the L infinity of x. So lambda g A lambda g star will give actually the action of g. So g will act on L infinity of x. So A circle g minus 1 is exactly that induced action. An important fact is that this phonema algebras admitted trace. So x, y commute inside a normal linear functional. And I will restrict my attention to phonema algebra that are factors. So that means they have trivial center. And to complete the terms that appear in the title, let me also say, recall it's a II1 factor. II1 factor is just a factor. It has a trace and is an infinite dimensional. And fortunately, II1 factors appear very natural by assuming these natural conditions. We get that L of gamma will be a II1 factor if and only if gamma is ICC. And we also have some sufficient conditions. If the action is free and ergodic, the associated group measure space for Neumann algebra again will be a II1 factor. And now finally, let me say, recall what's a prime II1 factor. So M is prime if M simply cannot be written as a tensor product of two I factors P1 and P2. And a quick remark is that if gamma is a product group, gamma 1 times gamma 2, then clearly L of gamma will not be prime, will have this decomposition. So if you want to find II1 factors that are prime, we should look for groups that don't have commutation. And the first example goes back to the work of Popa in 1983. He showed that the free group factor on uncountably many generators is prime. It took over a decade to obtain the primeness of the separable free group factors when n is an integer. And this goes back to the result of G, and he used Voiculescu's free probability theory. A few years after that, Ozawa was able to obtain a generalization of G's results in two ways. So first, he considered not just free groups, but hyperbolic groups. And he obtained not just that the phonema algebra is prime, but is solid. Solid is something stronger than primers. It means that the relative commutant of any diffuse phonema subalgebra is amenable. And Ozawa obtained this result by using some subtle seesaw algebra techniques. A few years after this, Jesse Peterson showed that for groups that are non-amenable and their first L2 beta number is positive, he showed that L of gamma is prime. And he did this by using his methods that he developed on closable derivations. And shortly after, Poppa also gave a new proof of solidity for the free group factors using his powerful deformation rigidity theory. And let me just point out here this remark. So as I said before, if L of gamma is prime, then gamma is not a product of infinite groups. And here appears a rigidity phenomenon. We can see that L of gamma remembers the absence of a product decomposition of gamma. In other words, if L of gamma is the same with L of lambda, they are isomorphic for different lambda, again, lambda will not be a product of infinite groups. Let me also say a few words about II1 factors that are prime, but in the setup of group measure space for Neumann algebras. So in other words, if I consider a group action, let's see some primeness results. So we actually have the following general statement. For any free ergodic PMP action, gamma acting on X, the associate for Neumann algebra L infinity of X cross gamma is prime whenever, and here are a couple of results. Ozawa showed that whenever gamma is hyperbolic, Kifan and Hudaye, by developing some new Basser type rigidity results, they show that this is true whenever gamma is an arbitrary free product group. And then Hoff also showed that for any free ergodic PMP action of a non-immutable group with the first L2 beta number positive, again, gives you a prime II1 factor. All right. One remark is that in all these results, the group gamma can be seen that has a rank 1 property. It either has some negative curvature condition in the form of a geometrical assumption, like hyperbolicity, like in the Ozawa result, or maybe some cohomological assumption, like in Jesse's result, and then in Dan's result, the L2 beta number is positive. Now appears a natural question. What can we say about the primeness of phenomenon algebras that arise from some higher rank type groups? And the first result that I want to emphasize it is a result in joint work with Dan Hoff and Adrian Yona a few years ago. So we showed that if gamma is an ICC irreducible lattice in a product of n connected non-compact rank 1 simple Lie groups, so rank 1 is the essential here information, then L of gamma is prime. And I want to mention that this is the first examples of prime II1 factors that arise from lattices in higher rank. Let me quickly recall what's an irreducible lattice. So gamma in a product of simple Lie groups, we say it's irreducible if the homogeneous action G acting on G mod gamma is irreducible, meaning it's separately ergodic. Each GI would act ergodically. And a quick example, for instance, we can consider PSL2Z adjoint root of 2. This would be prime whenever n is at least 2 square free and doesn't equal to 1/4. For the remaining of the talk, it will be useful the following definition. More generally, we can say that a product group is called irreducible if each of the GI is acts ergodic. All right. Now also we can think about a similar question. So we can make this analogy, again, to group measure space for Neumann algebras. What can we say about the primeness problem when we consider actions of groups of higher rank type? So here we can, we have the freedom of imposing maybe certain conditions on the actions. For instance, Poppa obtained a very general result for Bernoulli actions. He showed that any Bernoulli action of a non-amenable group gives rise to a prime II1 factor. So here gamma clearly can be a higher rank type group, irreducible lattice, and so on. And he obtained this result by using his spectral gap rigidity principle. Another class of specific actions, you might want to look at profinite actions or compact actions. Very recently, actually, Isono and Maraki, they show that L infinity of x cross gamma is prime for all fair-ergodic PMP profinite actions, or even more general, compact actions. And gamma is, let's say, SLN Z with NLS 3. And they use some essential ingredients from the literature. From Jesse Stock, we learn about properly proximality. So in the work where this was introduced by himself together with Adrian Yana and Rémi Boutonnet, they showed so-called double star rigidity results for von Neumann algebra that arise from profinite or compact action. And using that result and also Yana's cocyclen and orbit equivalent superrigidity result, they were able to obtain these primes. But now I want to go further. I want to look now at a different class of actions. So that are not just Bernoulli or compact actions. So what I'm going to do, I will look to a certain class of product groups, and we want to analyze when exactly an action of that product group will be prime or not. So let me start by introducing the following class of groups. We say that gamma belongs to the class C if one of the following condition holds. We can assume gamma is an ICC hyperbolic group, or we can assume that gamma is an arbitrary free product group, or gamma is a Reef product group, and sigma naught is the basis amenable, and gamma naught is non-amenable. The result is the following. If gamma is a product of n such groups, so each of the gamma I is hyperbolic free product of Reef product. Now let's continue by taking an arbitrary free-ergodic PMP action. The result is saying that the associated von Neumann algebra will be prime for any irreducible action. So whenever each of the gamma I acts ergodically. Moreover, if we assume in addition that gamma I belongs to class C and has property T, for instance, there exist hyperbolic property T groups like lattices SP N1, NLS T, NLS 2. The associated von Neumann algebra will be prime if and only if the initial action doesn't split. So if and only if the action does not admit a direct product decomposition. And this will be the first result for which this will be the first class of product groups for which the primeness problem for the action will be settled. Let me continue now by mentioning that for these prime to 1 factors that appear here, we can also have a unique prime factorization result. Before mentioning the result, let me just make this quick notation. So if gamma is a product group and T is a subset from 1 to n, we simply denote by gamma T the products of gamma I's when I is in T. And the result is the following. Let's assume gamma is a product of n groups that belong to the class C, and each of the group has property. Now let's consider an arbitrary free-ergodic PMP action, and let's denote by M the associated von Neumann algebra. What we can get is the following. We obtain that these groups that appear here, gamma 1, gamma n, they can somehow be splitted. So we get a partition from 1 to n, and we can look to each set Si. So we can look then to each group gamma Si, and we can find a certain action for each of the gamma Si. So this is a restricted product group. And what we obtain is that if we do the direct product of this action that we obtain, the direct product is actually the same with the initial action. So the initial action means this decomposition. Each of these actions that we constructed here in the conclusion will actually give us a prime to 1 factor. And this tells us, for instance, that M admits a prime factorization. It can be written as M1 tensor dot M. Moreover, we have actually a unique prime factorization, unique in the following sense. If M can be written as the tensor product of other K prime to 1 factors, what we must have is that this PI must be isomorphic with one of the MIs. This isomorphism happens up to unitary conjugacy inside the ambient algebra M and up to amplification. I want to mention that there are other unique prime factorization results appeared in the literature. I will just mention the first one that Ozawa and Popa obtained in their pioneer work, the first unique prime factorization result. And what they did, they actually obtained the moreover part true for the tensor product of L of gamma 1 with dot L of gamma k, and each of the gamma is ICC hyperbolic. In other words, if this tensor product equals P1 tensor Pk, L of gamma I will identify with Pi. In the remaining time, I think I can talk a bit about the proof. So I'll need the following notation. Again, we denote by gamma t the product of gamma I with i's in t. For a PMP action, we denote by elephant of x power sigma the subalgebra of fixed elements of elephant of x, where sigma is a subgroup in gamma. And we also make the notation P D symbol Q, saying that P intertwines in Q in the sense of Popa, or a corner of P embeds into Q inside the ambient algebra. Let me just recall the results. The result we've seen a few slides ago. So I'll just read it quickly. So we have a product group with groups in the class C. We consider an action. So we want to show the associated phonometric is prime when the action is irreducible. And under this extra condition, we want to show something more, that the associated phonometric is prime if and only if the action does not split. The proof will use a number of results or techniques from Popa's deformation rigidity theory. Let me start the proof by fixing again the notation. So we consider gamma a product group. Gamma I is in class C. We consider a free-ergodic PMP action. And let's just assume that the associated phenomena algebra admits a tensor product decomposition. So the idea, in other words, would be to classify the tensor product decompositions of L infinite of x cross gamma. They are here. I think I can say there are two main ingredients. The first one is that P1 can somehow be separated than P2 in terms that P1 can be embedded in the sense of Popa in L infinite of x cross gamma T1, and P2 will be embedded in L infinite of x cross gamma T2 in the remaining groups. This information will be essential for obtaining the fact that L infinite of x can be embedded in the fixed points of L infinite of x power gamma T1 and then with gamma T2. And this information should be read something like up to a finite index L infinite of x equals this algebra, this joint algebra. And now let's see how this should be enough to obtain our results. First, if gamma is irreducible, we obtain a contradiction simply because L infinite of x is diffuse. And the contradiction will be from the fact that we assume this is not prime and we consider decomposition into Tron factors. Secondly, if we assume that the gamma I has property T, we can actually obtain from the second step, we can obtain that there is a true equality. The true equality will give us actually that automatically that our action admits a direct product decomposition. And moreover, what we can say, we can also relate P1 and P2 with these new algebras, smaller algebras. So we can say that P1 is isomorphic with the L infinite of x power gamma T2 cross gamma T1. And this last result will be important for the unique prime factorization result. Okay, I think I'm exactly at time, so I will stop here. Thank you for listening.